Welcome learners. In today's lecture, we are going to look into the second order circuits, also known as RLC circuits. We are going to understand the behavior of voltages and currents that arise when we have resistor, inductor and capacitor connected together in a single electric circuit. So we are going to basically discuss two kinds of circuits. The first one will be a parallel RLC circuit and the second one will be a series RLC circuit. And for these two configurations, we are going to look into the natural plus the step response, and again for the series we are going to look into the behavior of natural plus step response of the circuit. And we know how the circuits behave in terms of voltages and currents when we have a natural or a step response. We saw these kind of circuits when we were talking about the first order circuits, which just had a resistor, inductor or a resistor with a capacitor configuration. But for the second order circuits, we are going to see the same behavior of the natural and the step response in terms of their voltages and currents, but we have now resistor, inductor and capacitor in a same configuration. So if we look at the natural response of a parallel RLC circuit, so it will have the following configuration, where we'll have the capacitor, the inductor and the resistor connected side by side, which we call as parallel to each other, and we are going to find the output voltage as a start for this natural behavior. We know that finding the voltages is the easy step when we have elements connected in parallel branches. So in this scenario, we are going to look into the derivation of the voltage expression, and we are going to see what happens when the elements, storage elements, capacitor and inductor release their energy. And this configuration represents the natural response because there is no voltage source connected to this, or we say that a sudden voltage source has been abruptly disconnected. In terms of the step response, what is going to happen is, for the same circuit, we are going to now introduce a switch and a current source. So now when the switch is at time equals to 0, the current is going to circulate among these branches, and thus when a certain source is attached, a certain DC source is attached to this network, we are going to see what happens to the voltage appearing now, and this type of configuration is known as the step response of the RLC circuit, which is connected in parallel configuration. Similarly, for the series circuit, we are going to have, so for the series RLC configuration, if we are talking about the natural behavior or the natural response of the circuit, so we are going to have this kind of a configuration where we have a resistor, an inductor and a capacitor all connected in series. And since this is a natural response, the easiest way to first find will be the current in this circuit, because the current remains the same in a series configuration. And since there is no source connected to this, so we call this configuration as a natural response of the circuit. And again, we are going to find the behavior of the current in case of the series response or a natural response of series configuration. And similarly, when we have this circuit and we introduce, let's say to this circuit, a source, in this scenario it is going to be an independent voltage source, and at time equals to 0, the voltage is going to provide energy in the flow of current to the RLC circuits connected in series. So when we connect a voltage source abruptly a DC source, voltage source is connected to this RLC series combination, we say that now we are going to do the step response analysis of this series RLC circuit. And again, we are going to begin our analysis by finding the current or the unknown current variation or the expression, since it is common between these elements. So these are the four categories of the natural and the series or the step response for two configurations of parallel and series that we are going to discuss on. So let us first start our discussion or finding the expression for the natural response of the circuit, and we begin our analysis by looking into the natural response of a parallel RC circuit. So we begin our analysis and understanding the natural response of a parallel RLC circuit. And again, in this topic we are going to figure out the unknown voltage that is appearing across the elements connected parallel to each other. So our basic configuration will be as such. So we will have a capacitor in parallel connected to an inductor, and then it will be connected to a resistor. And since all these elements are parallel connected to each other, we are going to first derive the expression for the unknown voltage which is appearing across the resistor, inductor and the capacitor. Keeping in mind that for these elements, since there is no voltage source, so what is going to be the energy available on these storage elements, which are capacitor and inductor? So the initial voltage appearing on the capacitor will be V0, initial current flowing through the inductor will be I0, and this was appeared because the what happened when the source was abruptly removed from this configuration. And now we want to figure out the equations for the unknown voltage when the storage elements are about to release their energy. So in order to do the analysis on this kind of a circuit, let us apply the KCL method on any of the node. And since the currents are flowing in this direction, IC, IL and IR, we are considering the default polarities. So the current enters the positive terminal. So when we apply the KCL on this circuit, so we know that the sum of currents should be equal to 0. So we can say that IC plus IL plus IR equals to 0. Now let us do the analysis and go side by side for easy analysis. So let us put the values of the current through the capacitor. So the current through the capacitor is C dV by dt. Then current through the inductor is 1 by L integration from 0 to t, the limits V d of t plus I naught, which is the initial current available in the inductor, and then the current through the resistor is as per Ohm's law, V by R equals to 0. Again, remember that this portion is the inductor model where we have the initial current I naught over here, and then what happens when the current starts to behave in a time instance from 0 to t. So if we differentiate this equation with respect to t, so we can say that d by dt, and then we have the complete equation C dV by dt plus 1 by L integral of V dt plus I naught plus V by R equals to 0. So once we do the differentiation, our equation will become C dV d square V by dt square plus the differentiation cancels out the integration, so we'll be left with V by L, and then I naught is a constant, so this becomes equal to 0. Then we'll be left with dV by dt 1 by R equals to 0. So this is the equation that we are getting once we multiply the differentiation inside the equation. So let us rearrange this equation, and since we are interested in finding the output voltage across the terminals of these three passive elements, so let us get rid of the capacitance. So we divide this complete equation by C. So we'll get d square V by dt square plus V by LC plus dv by dt 1 by RC equals to 0. And this is the equation that we are getting, and let us call this equation as equation number A. So this is the equation we are getting. If we do the analysis of this equation, we see that this is a second order equation. And how do we know it's a second order derivative equation? Because the power here is of exponent 2. Another thing to note or to identify if any equation is for the first order or second order circuit is that you should look into the equation. If the exponent power is 2, it resembles or it identifies that the equation is a second order differential equation. So this equation A is a second order differential equation. Another point to notify whether the equation is second order or not, if we see the equation and we see that both inductor and capacitor are part of the same equation, then it notifies us that this is a second order differential equation, or this is a second order equation or second order circuit equation. So now let us see how we can solve this. So in order to solve this equation, we cannot apply the separation of variables method. So we have to come up with another strategy. So another strategy is that we come up with an assumption to solve this second order equation A, where we consider the assumption in the terms of the unknown voltage. So we take an assumption to solve this equation. We say that the generic expression of the unknown voltage will rely on this assumption, where we say voltage is equal to A e power s of t. And let us say this is our assumption, we call it equation B. Now how did we reach to this assumption? It's very simple. So if you remember in the first order equations, especially for the natural response, when we were finding the RL and RC equations, so for the RL and RC equations, the output equation for the RL natural response of first order circuit came out to be of this form: I naught e raised to power minus t by tau, where tau was the time constant L by R. Similarly, when we found the natural response of an RC circuit, the voltage was having this expression V naught e raised to power minus t by tau, where in this case the time constant was RC. So looking at these first order equations, we can assume that if we go from the first order to the second order, we are going to have an expression that will involve a constant, let us say representing I naught and V naught with a constant, and the exponential is going to be there with a power sign. So based on this assumption, we came up with this equation B, where we can say that the constant I naught and V naught is represented by A, and exponential is going to be there, and the power can be positive or negative. The power can become positive if we consider an unbounded response. So generically we can make this assumption, and it is validated for the second order circuit. So in this way we got this equation B, which is assumption coming from the first order RC and RL circuits. So now once we have this assumption, let us put equation number B back into equation A and see what we can further do with this equation. So when we input this equation back into equation A, our equation comes out to be, so let me write the equation, d square by dt square, and the value of V is A e raised to power s of t plus A e raised to power s of t divided by LC plus d by dt, value of V is A e raised to power s of t dt multiplied by 1 by RC equals to 0. Now once we do the differentiation, so the first equation comes out to be A s square e raised to power s of t, this is the second derivative, plus this remains as A e s power t divided by LC, and the derivation of this becomes, since A is a constant, it will come out, derivation will be s e raised to power s of t divided by RC equals to 0. So this is the equation which I am getting after differentiating the above equation. And if you can further simplify this equation, so I can take the A constant to be a common factor, then exponential power s of t, then I am left with s square plus s by RC plus 1 by LC equals to 0. And let me call this as equation number C. So this is now the simplified equation that we are getting. And now if you look at this equation, there are two possibilities. The two possibilities being that either this portion of the equation equals to 0, or the equation inside this bracket equals to 0. So if we take a e raised to power st equals to 0, then this means that a should be equal to 0. But if we take a equals to 0, then our assumption becomes 0, since voltage will become 0, and we have assumed that initially there is a voltage that is appearing across the capacitor. So this means that our assumption of taking a from this equation equal to 0 is not correct. So a will not be equal to 0. Now what about exponential e power s of t, whether it is equal to 0 or not? So we can see that the power of the exponential is relying on the value of time, and the time is going to vary from 0 to infinity. The only case when the exponential becomes equal to 0 is we take time equals to infinity. Other than that, we are not going to have a value of exponential equal to 0. This means the exponential cannot be taken to equal to 0, because if we take time equals to 0, then we get the exponential value equals to 1. So this means the only element that is going to be equal to 0 is going to be this term, which is s square plus s by rc plus 1 by lc equals to 0. So the value inside the bracket is the only term or only possibility which can become equal to 0. So when we look at this equation, which is equal to 0, we come to realization that this represents a characteristic equation for the second order differential equation. And if we have this characteristic equation having a power or exponent of 2, this can only be solved using the quadratic expression. So in order to solve this equation, since it is having a power of 2, we need to apply the quadratic equation to get its roots. So quadratic equation will be needed to find the roots of the above equation, since the exponent is of power 2, and these roots will give us the expression for the unknown voltage that we are interested to find. So the value of voltage for the natural response of RLC will be dependent upon the roots, which will be extracted from the quadratic equation because of the exponent of 2. So if we solve this equation, and let me use this portion. So now we are in this side. So in order to find the roots of this equation over here, we know that the quadratic equation is represented as, so since we have exponent of 2, so there are going to be two roots. S1 and S2 is represented by minus b plus minus b square minus 4ac divided by 2a, where this is the value of b. So here this equation will be b, this equation will be c, and obviously this becomes RA. So now if we use this equation and find the roots, so we can say that S1 and S2 will be minus 1 by, because S is taken as 1 by RC plus minus 1 by RC whole square minus 4 into C is 1 by LC divided by 2 into A, where S is value of A and we have taken this to be 1. So this is the equation that we are getting for the roots. So if we want to utilize the denominator from the 2 and bring it on the top, so the roots final representation will be minus 1 by 2 RC plus minus 1 by 2 RC whole square minus 1 by LC. And now this is the final representation of the roots, and we can further write the roots individually as S1 comes out to be minus 1 by 2 RC plus 1 by 2 RC whole square minus 1 by LC. So let us say this is my equation number 1, and the second root comes out to be minus 1 by 2 RC minus under root 1 by 2 RC whole square minus 1 by LC in whole of the. So these are the two roots of the above characteristic equation that is going to help us find the solution to the unknown voltage. And how can we apply these roots to equations? So if we go back to our initial equation, which was equation number C, and input the value of the root. So this the values inside this bracket, now we are going to replace it with its respective roots. So our equation for the voltage comes out to be A1 e raised to power S1t plus A2 e raised to power S2t, and this is the equation that we need, or this is the equation that we have derived. Let us call this equation number D, which is going to help us find the expression for the voltage when we are finding the natural response of the parallel RC circuit. So here equation number D is basically the equation that we are interested to find the unknown voltages of a parallel RC circuit, and we got this through the roots of the characteristic equation. Now this equation can be verified, equation number D can be verified because we took an assumption. How can we verify this? If we take the value of this equation, equation number D, so in order to verify this equation D, because we took the assumption of voltage in equation number B, what we can do is we can take the derivative first order and second order of equation D. So if I take dV by dt, it comes out to be A1 S1 e raised to power S1t plus A2 S2 e raised to power S2t, and if I again take its second derivative d square V by dt square, so it comes out to be A1 S1 square e raised to power S1t plus A2 S2 square e raised to power S2t. Now I take these two values and put it back in equation number A. So equation number A was basically this equation. So if you put this back in equation number A, you are going to get the same value of which is equation number D. So if I use these two equations and put it back to equation number A, my equation number A was the equation which was 1 by RC dV by dt plus V by LC plus d square V by dt square equals to 0. So you just put the above two in this equation and you are going to get back your same equation number D, which we have just proven. It comes out to be A1 e raised to power S1t plus A2 e raised to power S2t. So this means that our assumption in the beginning was right, and hence we can find the voltage of a parallel RC circuit using this equation. So now let us see what information do we have inside of this important equation number D, which is also shown over here. So this equation basically gives us a few constants and few exponentials. So we can say that this equation is having constants A1 and A2. So A1 and A2 is basically figured out as the initial conditions of voltage and initial condition of the currents that we are going to see later on. So in order to find the initial values of the voltages and currents, we can find A1 through these values. And what about S1 and S2? So S1 and S2 are basically the roots of the equation whose values are figured out by the provided RLC values, and these things are going to be cleared when we move towards an example. So coming back to these roots especially, so what about the S1 and S2? Is there another way to write these two equations? Yes, in most of the literatures you are going to see an alternate version of equation number 1 and 2, which are the roots S1 and S2. So the S1 and S2 equation can also be written in this form, which is minus alpha plus minus alpha square minus omega naught square. So this expression is also the same as we saw here in equation 1 and 2. How this equation appeared? So we have considered the value of alpha to be 1 by 2 RC, and omega naught is basically 1 divided by under root LC. So in this equation 1 and 2, if you replace 1 by 2 RC with alpha and 1 by under root LC by omega. So you get this equation number 3, which is an alternative representation to find the unknown roots, which are S1 and S2. Now what is this alpha and what is this omega naught? So this alpha is called the Neper frequency with the units of radian per second, and this omega naught is called the resonant frequency or resonating frequency, and again its unit is radian per second. Similarly, the units for S1 and S2 is going to be radians per second, and this is basically your complex frequencies. So this is something that you might find in few books as well. So now what is this resonating frequency and this Neper frequency? So we can understand this in a very simple way. Whenever we have any sinusoid signal, we can see that L and C is something that keeps on resonating unless and until they have released all of their energy. So if we go back to our initial natural response figure, we can see in this circuit that the value of C and L, which is basically the storage elements, will start to release their energy until and until all of the energy has been released or they have reached their steady state condition. So if we try to plot this kind of a behavior for L and C, we see that the omega naught is basically dependent upon L and C, and we call this as a resonating frequency. This means our circuit will keep on resonating, or it will form a sinusoid until and until it reaches its final value, which is the steady state condition. So this behavior comes out in the form of a resonating frequency, and we call this as an omega naught. On the other hand, alpha is the Neper frequency, or we call this as an attenuation of the signal. Attenuation of the resonating frequency, which means that if any signal is resonating, let us say over here, so the Neper is basically going to help us in bring back this signal to a zero, or it is going to decay the signal. So if this is our signal, the value of alpha is going to bring this in a decaying fashion, and you can see the amplitude will almost equal to 0. It will become very less. So this is what it means by the Neper, the value of alpha or Neper frequency. So resonating frequency is the behavior of LC, and it keeps on resonating, and alpha is basically the Neper frequency, which tries to decay the signal in terms of the amplitude and bring it back to 0 or the steady state condition. So in both of these equations, when they combine, they gave us the roots, which are specific points on these sinusoids, and this is something you might have studied when you were understanding the quadratic equation. So what are the roots of the characteristic equation? Basically these are the specific points which help us know that what happened to signal at that instance. So this is how, when alpha and omega work in coherency, these resonating signals can be brought back to its final state or steady state condition when the Neper frequency plays a role in attenuating the signal. So hopefully this comparison between the resonating frequency and Neper frequency is clear. Now once we have this understanding clear, let us look at what else can we do with these forms of resonations, which means that let us compare or the behavior of Neper frequency and the resonating frequency omega naught. So there are three possible ways the sinusoid waves or the behavior of RLC can be mapped, and that is known as the three forms or possibilities of roots in the second order circuits. So if we go back to this resonating graph, we can also represent this LC and alpha in terms of the effect of R, L and C on any sinusoid signal. So we know that if the signal is having only the component of L and C, our signal is going to keep on oscillating unless and until it reaches its steady state condition in the natural response. But if we talk about the resistor in this circuit acts as the alpha, where it causes the damping in the signal, which means that it is going to try to bring the amplitude to 0 as quick as possible. So this is how the resistor is going to work in the RLC circuit. So resistor is known as the damping element in the RLC circuits, and this damping is also equal to the behavior of alpha. So now let us see what happens if we have the explanation in terms of the resonating and the Napier frequency. So there are three possibilities. You can see a waveform being generated by an RLC circuit. The first condition is that when your omega naught square is having a value less than the alpha square. The second behavior is when your omega naught square is having a value greater than the Napier frequency. And the third criteria is that your omega naught signal is equal to the alpha or the Napier frequency. So these three conditions basically give us an idea how the signal is going to propagate inside the RLC circuits. So let us see what these are. So when the omega frequency condition 1 is greater than alpha square, we say that this kind of a condition is an overdamp response. Overdamp response, and in this response the values of roots S1 and S2 will be real and distinct. So the values will be real and distinct. In the second condition, when the frequency or resonating frequency is greater than the Napier frequency, we say this is the underdamped response. In underdamped response, the values of roots S1 and S2 will be complex and conjugate. Again, these are written based on previous experiences when we did the analysis of this circuit. And when omega naught and Napier frequency become equal, the graphical behavior will have a critical response. And again, in this case, the roots will be real and equal. So these are the important things where we need to remember. These are the three forms or possibilities of the roots for the second order circuit. Now what does this mean? So again, if we want to plot these behaviors, this is what is going to happen. So let us say this is the behavior of our circuit, or okay. So this is the time axis. Now we are looking at the behavior of the voltage or current. So it can be any of these two for the natural response of an parallel RLC circuit. So this is a parallel RLC circuit, and we want to see or understand these three conditions of overdamp, underdamp and critical damp. So if the condition is 1, and the circuit is an overdamp, so what does it mean? So for the overdamp circuit, we basically say that voltages and currents are approaching its final value without oscillation. So if this is my maximum value, we say that the voltages and currents have basically reached their steady state or final value without oscillation. So this kind of behavior is known as overdamp response, and you can see the oscillation is not happening. When we say about oscillation, we means 1 cycle by second. So if this is any sinusoid, one complete oscillation is 1 cycle. So it will have a complete cleft and cleft. So we say this is 1 cycle per second, or normally we call this as 1 frequency with the unit of hertz. So you can see in the overdamp, the oscillation is not complete. We just have one positive or negative peak in this case, and it has reached back to its final condition. So if this is the graph, you will immediately say that this is an overdamped response of the RLC circuit. So we can say the condition will be that omega naught square is having a value of less than Napier square. What about the underdamped second condition? In the underdamped response, we say that the voltages and currents oscillate and they have reached their final value. So in the underdamped response, we can say that if this is the final value, the signal has basically started to resonate, and after some time with the amplitude decreasing, it has reached to its final value, and this is basically the overdamped underdamped response. So this is the underdamped response where omega square is greater than the alpha square, and you can see the sinusoid is happening in a complete way. So the value of voltage and current basically reaches its about, or it oscillates about its final value. So this is called the underdamped. And finally, the critical damped response is that the signal was about to be, or it is on the verge of oscillation. So for the critical damped response, we say it is about to start, but it reaches its final value. So you can see from this point, it just started and then it reached its final value. So this is called critically damped, where we have frequencies equal to each other. So this is the behavior of the waves or sinusoids when we are dealing with the RLC circuits, keeping in mind that LC will make your circuit resonate until it fades out, and R acts as a damping value and it tries to bring the resonance quicker to the steady state before the whole of the energy is released. So this is how the RLC circuits behave, and this is the way to represent them in terms of the Neper frequency and the resonant frequency. Let us look at an example and see how can we find the roots of these equations. So we take any example to understand the behavior. Let us say we have a simple natural response of a circuit with a capacitor, inductor, and a resistor. So this is R, this is L, and this is C. And we are given the following conditions: for resistance having the value of 200 ohm, inductor is 50 millihenry, and capacitance is 0.2 microfarad. And we have been asked to find the roots of this circuit, which means we need to find S1 and S2, and we also need to explain. So in the part A we find the roots, in the second part what kind of response is this, or the response of the circuit. Is it underdamped, it is overdamped, or it is critical damped? So we have been asked these two things. So let us solve this problem or example. So what we can do is, we know that the initial voltages are V0 and the currents are I0, and the current flowing is IR, IL, and IC. So in order to find the roots of this equation in the first part, we just go back to our equation or the simplified version, which is equation number 3. We know the roots depend upon Neper frequency and the resonating frequency. So we just need to find those. In order to find the roots, we need the help of these three circuit elements. So we need to basically find the roots S1 and S2, which is minus alpha plus minus alpha square minus omega naught square. This is the equation that we need to fill in the values with. So in order to find S1 and S2, we need to find alpha, which depends upon 1 divided by 2 RC, and the omega naught is equal to 1 divided by under root LC. From here the omega naught square is 1 by LC. So once we input the values of R, L, and C, we easily get alpha equal to 1 divided by 2 into R is 200 and capacitance is 0.5 micro. So it comes out to be 1.25 in 10 raised to power 4, the unit being radian per second. So this is the value of the Neper frequency. Similarly, the resonant frequency comes out to be 1 by LC square. Obviously, so it is going to be 10 power 8 radian per second square or radian square. So this is the two values that we have. So we basically look into the comparison of alpha and omega, and we see that omega naught square is having a value which is less than the alpha square. Thus this means that this response will be an overdamped response. So we have basically given the answer to the second part while solving for the first part, and then we conclude the first part by finding S1 and S2 by using this equation. So just input the value of the alpha square and the omega square. So S1 comes out to be minus 5000 radians per second, and S2 comes out to be minus 20,000 radians per second. So this is the solution to the first part, and thus we have solved the equation where we have figured out the value of the roots of the equation and whether the response is damped, over damped, or under damped. And we have seen the response is over damped because the resonant frequency omega naught is going to be less than the Napier frequency. Similarly, if we are asked to find the voltages of this or voltage of this circuit, so we can proceed by just applying the basic equation of voltage, which is A1 e raised to power s1t plus A2 e raised to power s2t, and from here we can find the voltage if we are asked, because we already know the roots s1 and s2, but we need to still find A1 and A2. And in the coming lecture we are going to look into how to find these constants A1 and A2.